Hello everyone, this is a quick video on another way of doing this sort of problem where you have an unexpanded polynomial and you're trying to solve it for a given trying to find the coefficient for a given exponent value in the expanded polynomial. You will have learned Newton's binomial theorem, and it can sort of be applied to trinomials like this where we have three numbers, but it's not necessarily the best. So I'm going to show you another way of thinking about it that might make it easier. So first, let's take it and let's expand it out. We have x to the 4 plus 6x to the 0, which is 1, so just 6, plus 8x to the negative 3, and of course all this is to the power of 7. And so now we know that when we expand this out, we're going to have this just 7 times. So another way of looking at that is each value in the expanded thing will be the product of 6 choices from this group of, in this case, 3 elements. And we want that final value to have an exponent of 2. So if you know how exponent multiplication works, you can say that we have a 4, a 0, and a negative 3. And that's these 3 values here. We have an x to the 4, we have an x to the 0, we have an x to the negative 3. We choose 7 of the members of this group, and it will end up with 2. So how do we get to 2? Well, let's start by, we're at 0, so we need to count upwards first. Let's add a 4. Now we're too high, so we'll subtract 3. Now we're at 1. So let's add another 4 and subtract another 3. Now we're at 2. And we don't want to move around from here, so let's add 0 and 0 and 0. And that gets us 7 elements. And when we add them all up, we get to 2, which is what we want. Now we know the pattern that we need. We need 2 of the x to the 4, 2 of the x to the negative 3, and 3x to the 0s. So let's see how many ways we can do this. Each resulting value is 7 elements chosen in order. So first, 2 of the elements have to be x to the 4. So we have 7 choose 2 elements, which will be x to the 4. So we choose x to the 4 2 times. And then we'll have 5 slots left over, of which we choose 3 to be x to the 0. So we have 6x to the 0, which we choose 3 times. And then last but not least, we will have 2 choose 2, which is 1 slots left. And in those slots, we will have 8x to the negative 3. And we choose 2 of these. And so if you work this out, you can see that if you compare it to the binomial theorem, we have the number of instances of the pattern, as we do in the theorem. And then these other 3 values are the second half of the binomial theorem, which is the actual values that we chose, to the power of the number of times each value was chosen. And if we work this out, we will see that the ending value will be, I didn't calculate it, but it will be 7 choose 2 times 5 choose 3. And this is the number of instances of the pattern we want. And then it will be multiplied by 1 squared, 6 cubed, and 8 squared, because this would be the coefficient for any instance of that pattern. It's 8 times 8 times 6 times 6 times 6 times 1 times 1. And then the x's are x to the 4 times 2, x to the 0 times 3, x to the negative 3 times 2, and all that works out to be equal to 2. So this is another way of visualizing the problem, and it works for an arbitrary instance. One important thing to remember, though, is that there may be multiple patterns which get you to this final value. So if there are multiple patterns, you do have to account for all of the possible patterns, which would be simple. You just add up. You do this multiple times, and you add them all together. It's probably safer to use the binomial theorem, but if it's not a binomial, then this is another option. I hope this helps people. So yeah.